Hello everyone. Starting from today, we are going to apply Fourier series to solve a solution of PDEs. So we are going to start with the very simple heat equation. So this is the system of heat equation. This is a heat equation with the initial boundary conditions. So let's say first equation numbering 1 and second condition 2, third one 3, 4. Okay, here we want to get a solution of these equations. So try to find the solution. Try our goal. Our goal is to find u x t satisfying which is the solution of 1, 2, 3. Okay, let me see. Solution. Find a solution u x t of equation number 1, 2, 3, and 4. So we want to find the explicit solution of these equations. Well, so if G is given explicitly, then we may find the solution of equation 1, 2, 3, 4. Okay, so how do we find the solution of this? So here, then one try. Okay, there are many different ways. Maybe you know a method to find solution. If this works, then you can do that. In general, in partial difference equations, for partial difference equations, it's not easy to get solutions. So in this case, we want to find a specific form of solution. Okay. So which is separation of variables. So xt is separated by two functions, xx, tt. Okay. So x is a function of only x variable. T is a function of t variable. So try to find the solution of this. Let me call this as a star. Solution of a star, which is the form of uxt equals xxt. So here I separated uxt into product of two independent functions. Okay, one function is variable x, the other function is variable t. Okay, then so I don't know whether this is a solution or not. Then I want to plug in this one into star. Okay, so now, so for now assume that. So for now, just assume that this guy, let's call 5. So 5 is solution. A solution of a star. Okay, solution of a star. Well, okay, solution star, and also, and this x is now constant equals 0, and also t is now constantly to 0. So t is now constant equals 0. X is now constant equals 0. So f is non-zero function, t is non-zero function, because if I give the function g is this one, non-zero, if it's a non-zero function, so I give, if this is zero, then obviously zero solution. So let's see, gx is not zero function, then x, if x or t equals zero function, then does not satisfy. So for now, let's assume this u xx tt satisfy the star, and x is non-zero, t is non-zero. So this is our assumption. Then you want to compute the partial u, partial t. That would be xx t prime t. And you can also compute partial derivative with respect to x twice. Then this is x double x tt. Okay. So then the equation number one becomes x t prime t equals x double prime x tt. Okay. And then number two equation becomes, so you plug in here, then x0 t equals to 0. And the number three equation becomes xl t becomes 0. So this is for x between 0, l, t is positive. So this is for all t positive. This is also true for all t positive. And then equation 4 becomes xx t 0 equals g of 0. So this is what we have. So if we assume this uxt equals xxtt is a solution of this star, then we have these four equations. So let me call this is 1 prime. Let me call this one, 1 prime. I don't like a prime. So 6. So let's say 6, 7, 8, 9. Okay. So now since x is non-constantly 0, t is not constantly 0. So therefore there exists x. So I don't need x. Okay, let me erase this part. So here, since t is not constant equals 0, then there exists t0 is between positive such that t naught equal non-zero. Okay. So from here, so what we get from here, this is true for all t. This is true for all t. So you plug t0 in value here. That implies x since. So using this one, we have x. We have x0 since x0 t0 equals 0, so x0 should be 0. And also the same xl t0 equals 0, that implies xl becomes 0. Okay, so equation 7 and 8 becomes this condition. So we have, let me make a box here. This is a condition. So this is from 7 and 8. Okay. And then from equation 1, what I'm going to do, so equation 1 prime was, not easy to write down. So equation 1. So now we have xx t prime t x double prime x t is true for x between 0 L t equals positive. This is equation oops. Okay, so from equation 6, so we have this one, right? So now, so what kind of function xt satisfy this equation? Okay, this is what I want. So then what I'm gonna do is what I'm gonna do next is not mathematically rigorous. Okay, what I'm gonna do is this. Okay, just try to divide equation 6 by x double prime xxtt xtt. You cannot actually divide xxtt because for some point x or some point t, this could be 0. So that's why I told you this is not mathematically rigorous. Okay, so let's just try to divide. So then I have xx t prime t divide xx tt, and I have x double prime x tt, then xx tt. Okay, then you can cancel these two. So then we have a t prime t equal tt, and then x double prime x divided by xx. So we have this one, right? And then you look at here. So when you look at right hand side of this equation, this guy is a function of x variable. X. And then this is also, this part, function of t. So you have two functions. One function is a function of t. The other function is a function of x. They are the same. So then only possibility is that these are constant. So this implies this should be constant. Constant. So I put just the minus lambda. Well, you can put lambda, but just my choice. Minus lambda, and then lambda is constant. Okay. Lambda is constant, so real number. So we are talking about the function u xt are real, it's constant. So then, if this is constant, you multiply, then I have a t prime t equal plus lambda tt equals 0. I obtained x double prime plus lambda x equals 0. So I have two equations. Okay. in order to derive these two equations, what we did, in order to obtain these two equations, from equation 6, we divide 6 by xxtt, then we got this, and we have this one. Okay, so at the beginning, we divide this equation by xxtt, but this is not, I already told you that this is not mathematically rigorous, because at some point x can be 0, some point t can be 0, but somehow at the end, we don't worry about this one, right? So we have, at the end, we don't worry about dividing things. So from here, this is just a kind of method. Then I can prove that, you can prove that from this. Then if xx and tt satisfy equal equation t prime t plus lambda tt equals 0, x double prime x plus lambda xx equals 0, then xx t prime t equals x double prime x equals tt. Okay, for every x between 0, L, t is positives. Okay, so in order to find a solution of this guy, so we need to find this one. Okay, t satisfy this equation, x double prime, x satisfy x double prime plus lambda x equals 0. So we want, let me rewrite this one. Okay. So let me make a box here. So this equation. So this equation from where? Equation 6. Okay. This is from equation 6. So you see, this is easy to prove. Okay. Once t satisfies this equation, this is proved. So from previous calculations, what we obtained is this. So then we have equation x double prime x plus lambda xx equals 0. And then x0 equals 0, xl equals 0. And then we have t prime t plus lambda t equals 0. So we have this equation, these three equations. So these are from equation number 1, 2, 3. Okay. So finally, this one obtained from. So these are obtained from equation 1, 2, 3. You have to recognize that we did not use equation 4 yet. So then we have to find so from, let me call, this is the double star. Okay, let's see. So let me call, this is double star. Okay, so now you need to find the equation double star. So you need the background from ODE. From ODE, then do I need to explain? So I'm going to explain this, to find the solution of this one later. So here, if if lambda equals k pi over L square, then the solution xx could be any constant times sine k pi x divided by L. Okay, so A is constant. Here's the A is constant. And then at the same time, you solve this x and t, satisfy this equation at the same time. So then you got t equals, also t0, exponential minus k pi over L squared t. Okay, this is the equation what we have. So then uxt becomes xxtt, so xxtt. Anyway, t0 is constant. I call another constant a tilde e to the minus k pi divided by L squared t sine k pi x divided by L. And if lambda is different from k pi over L squared, then we have x should be just 0. Okay? But at the beginning, so we don't want to have x0 solution. So then this implies, and in this case u xt has to be 0, constantly 0, but this does not satisfy it. Right? This is not I want, so this is we don't want. So only solution of star is lambda should be k pi over L square, and then uxt is this. So we have many different solutions. Here k can be any natural number. So finally, from here, what we have. So we obtain a solution. Actually, solutions. There are many solutions. So solutions. Let this one is depends on k, so I can ukxt. So I call this ukxt. ukxt. K can be any natural number satisfying equation number 1, equation number 2, equation number 3. Okay, so at the beginning we have this is equation number 1, 2, 3 solution. Okay, but these solutions ukxt does not satisfy full. Okay, so we tried to find the separation solution uxxt in form 5. We obtained infinitely many solutions uk. Fortunately, this uk satisfy equation number 1, 2, 3, but does not satisfy the 4 condition. Okay, and then one can, then we need the we need a solution of satisfy all 4 conditions. And then one idea is this: because each of this one does not satisfy this, and then you can actually consider infinite sum of this one. You can consider series solution. Then we consider now let u xt is infinite sum, multiply k from 1 to infinity, and then I use multiply some constant and the u k xt. So I want this one to be solution. Okay, look, put this where and we want this is. This is equation 10. Okay, let me call this is equation 10. E1 u xt in equation 10 to be a solution of 1, 2, 3, 4. Okay, this is what we want. And formally, each UK satisfy equation 1, 2, 3. Okay, 1, 2, 3. Formally, I said formally. So formally means not rigorously proof, just sort of intuitively. So each UK satisfy 1, 2, 3 conditions, and then you multiply a constant ak is also satisfied. And then you can guess summation is also satisfied this. Okay, once uk is given, you can find the ak, then you can satisfy. And also you can differentiate this with respect to x twice. Then we need some more theory to prove actually you can differentiate with respect to x. They are the same. So there are a little subtle things to verify, but formally. So here I said formally. Formally means you need to prove rigorously later. Formally, u uxt satisfies 1, 2, 3. Okay, if here ak is not find yet, right? So for now we assume that 1, 2, 3 is okay, and then we from equation 4. So equation 4. This one satisfies equation 4. Equation 4 is this. Gx equals u x0. And then you plug t equals 0 here. That would be summation k from 1 to infinity ak u k x0. So then I got this one, k from 1 to infinity. Let me say, here, let me change notation. Okay, and then my notation is this one. So uk xt equals, I take a tilde equal 1, so exponential k pi over l squared t sine k pi x divided by l. This is also solution. Okay, solution, and you plug 0 here. Then I got here ak sine k pi x divided by l. So this is what we have. So in order for uxt satisfy equation 4, this should be equal. Okay, so this one is equal. So let me rewrite gx equals summation k from 1 to infinity ak sine k pi x divided by l. So this should be true for all x between 0 L. Okay, so we assume that G is continuous. Okay, So this is given. G is continuous function. And then when you look at here, so first you need to find AK so that this is true. So what is AK? So that's why we studied the Fourier series. Okay, this is actually Fourier sine series of Z. So this is Fourier. If I take AK equals 2 over L integral 0 to L gx sine k pi x divided by L dx. Then the right hand side, then summation k from 1 to infinity ak sine k pi x divided by L is the Fourier sine series. Of G on x between 0, L. Okay. So this is what we learned previous lectures. Okay. Then we assume that G is continuous. Let me assume more. Okay. I'm sorry. T is continuous. Also, I assume that G prime is piecewise continuous. Piecewise continuous. Then we assume that G is continuous and G prime is piecewise continuous. Okay. Then since G is continuous and G prime is piecewise continuous. So like piecewise continuous. Then you can apply Fourier theorem by Fourier theorem. Then this guy, the series, summation k from 1 to infinity ak sine k pi x divided by L, that x converge to gx. Converge means they're the same. Okay. So this is actually u x0. Okay. So here, where I just rewrite copy ak should be 2 over L 0 L gx sine k pi x divided by L dx. Okay. So then finally, we have the explicit form uxt equals summation k from 1 to infinity. So I find the ak set it here, and then e to the minus k pi over L squared t sine k pi x divided by L. This is a solution of equation 1, 2, 3, 4. Okay. So now in this form, we have an explicit form of AK because AK is given here, so G is given. So you can actually compute this integration, and then you have constant. Then we can consider this. Okay, this is a solution of 1, 2, 3, 4, sort of formally, right? Because although if each UK xt satisfy equation 1, 2, 3, at the beginning, in the middle, we assume that formally this is a solution. We assume this one. Where is it? Where is it? Formally solution. Did I erase this one? Here. Formally, this one satisfy 1, 2, 3. So here, so you need once this AK is given, I have explicit form, and then I need to show this is actually converge uniformly somehow. So here, solution, but somehow, we need to verify rigorously. Okay. Equation 4, okay, but 1, 2, 3. So we need to verify rigorously, but I'm not going to talk about this one. So today's lecture is about using Fourier series to find the solution of heat equations. Okay, so here today in this lecture, I didn't talk too much about finding this ODE, and this one will be, I will talk about this equation, will be in another lecture. And from this problem, there are many different kind of problems that you can switch the condition 2 by like this one, ux0t equals 0. You can also using this one here also uxlt equals 0. So you can use either this boundary condition or this boundary condition. For equation 3, you can use this condition or this condition. And also, so using these two conditions, you have 4 different type of problems, right? So let me take 2 prime, this 3 prime. You can take equation 1, 2 prime, 3, 4, okay? Equation 1, 2, 3 prime, 4. Equation 1, 2 prime, 3 prime, 4. So you have 4 different type of problems. So, but you can do the same analysis, exactly the same. You can follow the method, okay? So in the middle, if you take a different type of boundary condition here, then you will get different equation here. So you need to find this solution. So I will give another lecture to explain only this type of ODE solutions. Okay, thank you very much.